Assalamualaikum and hello to everyone. In this video, we will cover the remaining processes for subtopic 2.4 in chapter 2. For the fourth process, as you can see, for process name, there is no common process name as no property is held constant, and the thermodynamic name is called polytropic, and only for gases, it can be in terms of PV by the power of n equals to C, where n here can be any number between negative infinity and infinity, except for 0, 1 and the values for gamma. The process line for a polytropic process is a curved line. However, the difference between this curved line and the curved line for an isothermal process is the degree at which the curve is bending, which now depends on the index number n. And also, this process line is only valid for ideal gases. Okay, next is the boundary work equation. Similar with the isothermal process, the boundary work equation is dependent on the type of substance. Okay, so for phase change substances, water and refrigerant R134A, the boundary work is based on the area under the PV diagram. And for ideal gases, to calculate for boundary work, we can use the following equation. For first law energy equation, okay, start with writing the general equation, and to determine the amount of heat transfer, we can rearrange the equation to solve for it. For delta U, just like other processes, it can be expanded as shown in the video, and from now, students should know how to determine the values for specific internal energy based on the substance. Now, for the polytropic index, since n can be any numbers between negative infinity and infinity, provided that the question does not give the value for n, we can solve for n by using this relationship equation, okay, depending on the properties provided. Okay, so we can use three of these, either one, to determine the value for n. And also, this relationship equation is helpful, okay, to help us to find the properties such as pressure, volume, and temperature if it involves a polytropic process. Okay, now let's look at the first example for a polytropic process. Okay, you can pause the video to read and understand the question properly. Okay, like usual, for step 1, please try to draw the process schematic diagram based on the question. So we have a polytropic process, so state 1 and state 2, which is connected by the polytropic expansion process. And for step 2, okay, we write whatever is required or equations. Okay, so from the question, we have to calculate the amount of boundary work. So using the boundary work equation for a polytropic process. And for amount of heat transfer, we will apply the first law energy equation for the polytropic process. For step 3, okay, based on the equation, we try to find the required properties at each of the state. So for for state 1, we can calculate for the value for mass, which is required in the equation. And for state 2, we can calculate for the value for V, the volume, which is required also in the question. Okay, since this question involves a polytropic process and the value for n is not given in the question, so we have to determine the value for n. So using the relationship equation, so we can solve for the value for n. So the relationship equation we have chosen is between P and V. Because why? Because these are the values which are mostly provided in the question. So we can substitute the values and doing the required mathematical steps. Okay, so these are just basic mathematics here. we can calculate for the value for n, which here is equal to 1.25. And for step 4, okay, we have to only substitute the values which are required in the equation to calculate for the amount of boundary work and also the amount of heat transfer. Now for the final process, okay, similar to the polytropic process, there is no common name because none of the properties are constant. So the thermodynamic name is called adiabatic. Adiabatic here is another meaning for thermally insulated. In other words, the amount of heat cannot enter or leave the system. Therefore, Q net here is 0. And only for gases, similar like other processes, it can be written in the form of PV by the power of N equals to C, where N here is equal to gamma, which is the specific heat ratio Cp over Cv. For the process line, okay, similar to the isothermal and also polytropic process, the process line is also a curved line. The difference between this curved line and the other processes is the degree at which the curve is bending, which now depends on the value of gamma. For boundary work equation, similar to the polytropic process and isothermal process, for phase change substances, water and refrigerant, we have to sketch the PV diagram, and from the PV diagram, we must determine the area under the graph. And for ideal gases, we can use the following equation to calculate for boundary work. And if we look at the equation, the boundary work equation for an adiabatic process is very much similar to the polytropic process, only that instead of N, for adiabatic process, it used the value of gamma. For the first law energy equation, okay, start with writing the general equation. And since the process is adiabatic, which means Q net here is 0, we can cancel the term Q net and it will leave us with the equation negative work net equals to delta U. And this equation here can also be used to calculate the boundary work. And also delta U here can be expanded into the following equation, and just like the processes before, by now, okay, we should know how to determine the properties, okay, for specific internal energy based on the substance. So now let's look at the example for an adiabatic process. Okay, you can pause the video to read and understand the question properly. Okay, so in step 1, just like examples before, please try to draw and label the schematic diagram for the process in the question. So we have state 1 and state 2, and the process is an adiabatic expansion. For step 2, okay, based on the question, for the first item, we have to find the properties for specific internal energy at the initial state and also the final state. So this will be solved in step 3 later. And for the work input during the process, since we know that the process is adiabatic, we can use the first law energy equation and we can cancel the term Q net. So using the first law energy equation, we can calculate also the boundary work, the amount of boundary work. So for step 3, we start with state 1 to determine the required properties. So for state 1, okay, we have to calculate the specific volume first in order for us to check the phase of the substance. So using table A5 at 10,000 kilopascal, we compare the value for specific volume with Vg, which is greater, therefore meaning the phase is in the superheated region. And when the phase is in the superheat region, we have to look at table A6, and at table A6 at 10 megapascal, we locate where the value for specific volume is, and we can see that it's between these two values, this range of values. So by using the interpolation technique, we can calculate for the specific internal energy at the state 1. Okay, so for just a quick quiz, why don't you try to calculate the temperature at this state? We continue with the state 2. Okay, for state 2, similar to state 1, we have to calculate the specific volume first in order for us to check on the phase. So using table A5 at 1000 kilopascal now, compare the value for specific volume to Vg, which we see here is still greater, therefore the phase is still in the superheated region. And using table A6 at 1 megapascal, locate where the value for specific volume is, okay, inside the 1 megapascal table, and we see that the value is between these two range of numbers. And similar to state 1, we use the interpolation technique to determine the specific internal energy at state 2, and also try to calculate the temperature at this state. For step 4, we just have to substitute the required values into the equation to calculate for the amount of boundary work for this process. Okay, the next example is a combination process between isothermal and polytropic. Okay, so this is the second example for a combination process. Just like the first example, I would like just to remind you, whoever is listening, that please do not be afraid of questions which involve more than one process. Treat each process individually. Okay, and if the question asks to calculate the total amount, just add up the values which have been calculated individually, so that we can find the total amount. Okay, so don't panic. Okay, treat the question as if it's an individual process. Okay, so you can pause the video to read and understand the question properly. As usual, for step 1, please try to draw the schematic diagram. So for the first process, state 1 and state 2 is the isothermal process, because now the gas law is PV equals to C. So when PV equals to C, N here is equal to 1. Okay, so for state 2 and state 3 is the second process, polytropic process, and the polytropic index is given in the question 1.5. Okay, so for step 2, okay, for total boundary work for both processes is the total, meaning that calculate individually for each process the boundary work and then add them up to determine the total value. Also for total amount of heat transfer is the individual, okay, heat transfer, calculate them individually and then add them up to get the total heat transfer. So be careful with the state. State 1, kedua is the first process, state 2, ketiga is the second process. So for step 3, determine the required properties. So we have 3 states, so we start with state 1. Okay, so whatever properties that is required in state 1, we calculate. So we see here we need the properties for volume 1. So we use the equation PV equals to MRT. And for state 2, we need volume 2. So we calculate for volume 2. For state 3, okay, since it's a part of the polytropic process, so to calculate for volume 3, we have to use the polytropic relationship equation. Okay, so here we use the relationship between P and V because that is the which most values are given in the question. So using the polytropic index 1.5, we can substitute, okay, the values into the equation and calculate for V3, and only then using the ideal gas equation PV equals to MRT can we calculate for T3. Okay, so once we have all the values, pressure values and also volume values, we can sketch the PV diagram as mentioned in the question. So start by drawing the PV axis and then draw the process line for the first process. So process from state 1 to state 2 is the isothermal expansion process. Okay, you can label the properties here for V1 and V2 and also pressure. And then the second process line, okay, for the polytropic, which now from 2 to 3, the pressure at state 3 must be equal, okay, must be parallel with state 1. Okay, so we can read, we can label for V3 and also label the pressure exists. For step 4, okay, just substitute, okay, the values into the individual boundary work equation. Once we have calculated the boundary work equation answer, only then we add them up to get the total boundary work. Same with the amount of heat transfer, calculate them individually. Once we have calculated them individually, we can add them up to get the total amount of heat transfer. Okay, so we have come to the end of the video and also the end of chapter 2. Okay, so for exercises, okay, please refer to the original notes, and for additional questions you can refer to past examination papers. Okay, if there are any questions, please do not hesitate to leave a comment at the related forum section. Thank you for listening and have a good day.